Based on magnetic susceptibility and relative magnetic permeability of materials, they are classified into three categories, namely diamagnetic, paramagnetic, and ferromagnetic materials. Now, let us discuss the properties of these materials, starting off with the diamagnetic materials. Diamagnetic materials are the materials that are repelled by magnets. When a bar of diamagnetic material is placed in a non-uniform external magnetic field, it tends to move from a region of strong magnetic field to a weaker magnetic field. We also observe that the magnetic field lines are expelled or repelled by the diamagnetic material, and the magnetic field inside the material is reduced. Let us discuss the causes of diamagnetism. We know that the orbiting electrons around the nucleus in an atom are equivalent to the current-carrying loops. These electrons possess an orbital magnetic moment. For a diamagnetic material, the resultant magnetic moment of all the electrons in an atom is zero. When the diamagnetic material is placed in an external magnetic field, due to induced current, the movement of the electrons for which the orbital magnetic moment is in the same direction as that of the external magnetic field is slowed down, and the orbital magnetic moment of the electron decreases. Likewise, the movement of the electrons for which the orbital magnetic moment is in the opposite direction to that of the external magnetic field is sped up, and the orbital magnetic moment of the electron increases. The material then develops a resultant magnetic field in the direction opposite to that of the external magnetic field. Hence, the diamagnetic materials are repelled by the external magnetic field. Although diamagnetism is present in all materials, its effect is very weak in most of them. Some examples of diamagnetic substances are bismuth, copper, lead, silicon, and nitrogen at STP. Magnetic susceptibility of the diamagnetic substances is greater than or equal to -1 and less than 0. Relative magnetic permeability of these substances is greater than or equal to 0 and less than 1. Superconductors exhibit perfect diamagnetism. When a material is cooled below its transition temperature, it becomes a superconductor. In superconducting state, the material behaves as a perfect conductor of electricity and a perfect diamagnetic material. When a material makes a transition from the normal state to the superconducting state, it actively excludes the magnetic field from its interior and hence repel magnets. This is called Messner effect. Maglev trains, or in other words, magnetically levitated superfast trains, work on the same principle. Let us discuss about paramagnetic materials. Paramagnetic materials are the materials that are weakly attracted by the magnets. When a bar of paramagnetic material is placed in a non-uniform external magnetic field, it tends to move from a region of weak magnetic field to a stronger magnetic field. The magnetic field lines get concentrated in the paramagnetic material, and the magnetic field inside the material increases. Now let us discuss about the causes of paramagnetism. In case of paramagnetic material, individual atoms possess a permanent magnetic dipole moment due to the orbiting electrons in the atom. But, due to random thermal motion of the atoms, the net magnetic moment of the material is zero. When a paramagnetic material is placed in an external magnetic field of induction B0 at low temperatures, the magnetic dipole moment of the individual atoms align in the same direction as of the external magnetic field. Some examples of paramagnetic materials are aluminium, sodium, calcium, etc. Magnetic susceptibility of paramagnetic materials is small and positive. Relative magnetic permeability of these materials is slightly greater than 1. A paramagnetic material placed in an external magnetic field gets weakly magnetized. The magnetization of the paramagnetic material is inversely proportional to its absolute temperature. That is, I is inversely proportional to T. Let this be equation 1. The magnetization is directly proportional to the applied magnetic induction. That is, I is directly proportional to B0. Let this be equation 2. By combining equations 1 and 2, we get I is proportional to B0 by T. This equation can be written as I is equal to C into B0 by T, where C is the proportionality constant. Let this be equation 3. We know that B0 is equal to mu0 H. Let this be equation 4. We also know that the ratio of magnetization to magnetic intensity is magnetic susceptibility. That is, chi is equal to I by H. Let this be equation 5. Substituting equation 4 and 5 in equation 3. And on simplification, we get chi is equal to C into mu0 by T. This is known as Curie's law, where C is called Curie's constant. Let this be equation 6. Thus, the magnetic susceptibility chi depends on the nature and the temperature of the material. Since the magnetization of a material is directly proportional to the applied magnetic field induction and inversely proportional to its absolute temperature, the magnetization of a material increases up to a certain level by increasing the magnetic field and decreasing the temperature. At this magnetization, all the atomic dipoles are aligned in the same direction of the magnetic field. This value of magnetization is known as saturation value and is represented as IS. Beyond this value, Curie's law is not applicable. Let us now discuss about ferromagnetic materials. Ferromagnetic materials are the materials that are strongly attracted by the magnets. When a bar of ferromagnetic material is placed in a non-uniform external magnetic field, it has a strong tendency to move from a region of weak magnetic field to a stronger magnetic field. And the field lines are highly concentrated inside the ferromagnetic material. Let us discuss the causes of ferromagnetism. Similar to the paramagnetic material, the individual atoms in a ferromagnetic material also possess a permanent magnetic dipole moment due to the orbiting electrons. These individual atoms interact with one another and arrange themselves in a common direction over a volume of some millimeters. This volume is called the domain. Each domain contains about 10 to the power 11 atoms, and each domain has a net magnetization. The magnetization changes from domain to domain. Thus, the net magnetization of a ferromagnetic material is negligible. When a bar of ferromagnetic material is placed in an external magnetic field of induction B0, the magnetization of the domains orient in the direction of the applied magnetic field. When the external magnetic field is removed, some ferromagnetic materials can retain the magnetization, and such materials are called hard ferromagnets or hard magnetic materials. Alnico, steel, Ticonal, etc. are the examples of hard ferromagnetic materials. These materials are used to prepare permanent magnets. There are some other materials which can lose its magnetization when the external magnetic field is removed. These materials are called soft ferromagnetic materials, and they are used to prepare temporary magnets. Iron, cobalt, nickel, etc. are the examples of soft ferromagnetic materials. The magnetic susceptibility of ferromagnetic materials is positive and very much greater than 1. The relative magnetic permeability of these materials is also positive and very much greater than 1. Now, let us discuss an activity to know the effect of temperature on ferromagnetism. Let us consider an L-shaped wooden stand and fix a strong magnet on top of it. Consider a ferromagnetic material, say, a nickel paper clip tied to a string which is fixed at the base of the wooden stand. Let the paper clip be suspended in air with the help of a magnet as shown. Now, heat the clip with a lighter to increase its temperature. At a particular temperature, the paper clip falls down. That is, at that temperature, the clip transforms from being ferromagnetic to paramagnetic. This transition temperature is known as Curie's temperature. In other words,